Okay, so just to let me introduce myself shortly. My name is Diamant. I am an AI consultant in the fields of Gen AI and computer vision. And today I'm going to talk with you about a combination between RAG and agents and how we're going to solve together complex tasks, which we can also control what's going inside. So our agenda for today is going to be shortly talk about what is RAG, a short recap, then very short introduction of what are agents and why should we control them. And then we're gonna build together how we're gonna get an agent that we can control that performs RAG tasks. And eventually I'm going to show you a short demo about it. So our use case is going to be the first book of Harry Potter. And the reason that I chose this is because Harry Potter contains a complicated plot, which you can ask non-trivial questions about it. And using regular RAG is going to be impossible, very difficult to impossible to solve these kind of questions. So what's RAG? RAG is a short, it's an acronym for Retrieval Augmented Generation, which is a method that helps AI language models to generate text based on external information, your custom data, and other kind of data resources. So the common mechanism of what people usually do in RAG is to take your data, in our case is the Harry Potter book. You want to split the book into many chunks. You can choose the size of the chunks, but you split it into many different chunks, and then you take those chunks and you embed them into a much lower dimensional space and store it inside what's called vector store. Then, when you get a query of the user, you input it into the system, and the query is also getting embedded into the same lower dimensional space, and it's compared to the information that's inside already the vector store. Then you retrieve the information to get a context that you're going to insert to the LLM together with your query to get the final answer that's going to be based upon your context and not upon the pre-trained knowledge of the LLM. So agents, LLM agents, are advanced AI systems that are designed for creating complex tasks that need sequential reasoning. And they can think ahead, they can remember past conversations, and they can use different tools to adjust their responses based on the situation and the style needed. All right, so why do we actually need to control such an agent? And the simple answer is there is a trade-off between the agent's level of autonomy and the control that you have over the process. The more autonomy you give to the agent, the less control you have. And so if you're using a regular agent, we don't have control over when it uses its tools or in what order. And we cannot control the conclusions it derives from the tools. And especially it's very hard to trace hallucinations that you have inside the mechanism and or the use of pre-trained knowledge used by the LLM. But when you're using a workflow engineering that you construct the flow and how the agent is going to work, so you're defining your specific path of how to tackle the problem. You have a full control over each step, or at least you want to. But this is a but. It requires a tailored solution that might be time consuming, and you have to fine-tuning very carefully to your problem, and it might be complicated. All right, so covering this, which building blocks do we need to create a controllable RAG agent? So just going a little bit back to the basics to talk about semantic similarity, that in our embedding space of we embed all the data, the embedding space is sorted in a way that words that are similar to each other are going to lay close to each other, which means, for example, that the word king and queen are going to be closer than the word dog. And I said this because in a simple RAG problem, we can use this functionality. For example, if we have the query, what happened in France on July 14th, 1789, and we have a large corpus of historical events. So we may encounter in our data a sentence or a chunk that says on July 14th, 1789, the storming of the Bastille, etc. So this is very similar to each other, and it's going to be a simple task to retrieve this as our context and get our final answer from this. But what happens if we want to deal with a little bit more complicated questions, such as, in our case, in Harry Potter, how did Harry beat Professor Quirrell? So in our data, we're not going, in the first book of Harry Potter, there is not a sentence that says, Harry beat Professor Quirrell by doing this and this and this. And for this, we have to think about how we're going to construct our data differently, maybe. So we can create the book chapter summaries also using an LLM that may contain some keynotes and summaries of the chapters, which there it's more probable to find the solution for such a question. All right. On the other hand, if we want to be very precise, if we want to ask, according to Hermione, what is worse than being killed? And there is this very popular quote from the book that Hermione says, we could have been killed or worse, expelled. And to get this kind of resolution, we also have to think how we're going to construct our information, since if we're embedding large chunks, the embeddings are going to be different than the embeddings of such specific quotes. So we can also take all the quotes from the book and construct and embed them also inside a book quotes vector store. So in this case, in our case, we have 3 different vector stores: the chunks vector store, the chapter summaries, and the book quotes vector store. All right, so until now, if we want to think about a naive flow engineering that an agent can validate the RAG pipeline, we can input some query, then we want to retrieve the context per this query, the question, and then we want to filter out all the non-relevant information from this context. Then we can verify whether it's not relevant and then rewrite the question. And if it is relevant, we want to answer the question from the context and verify it's not hallucination. So as long as it's a hallucination, we want to do it again. And if it's not useful, we can again rewrite the question. And if it is useful, we can output the final answer. And this can be easily designed using LangGraph. I use this, I really recommend this. It's very easy to use. You can define your edges and vertices and then construct this with LangGraph. And so we could have been finishing this lecture at this point, but we still want to be able to solve more complex questions. So, for example, how did the protagonist defeat the villain's assistant? we have no idea which book it is. We don't have any information about it. So in order to solve it, we need to first identify the protagonist of the plot. Who is it? Then we need to identify who is the villain. And then to identify who is the villain's assistant. Then we have to search for any kind of confrontations or interactions between the protagonist and the villain. And only finally, we can try to deduce the reason that led the protagonist to defeat the assistant. So in order to do all of this, we may need the following capabilities. First, we need to have tools for this agent. Second, we want to have a reasoning ability. We want to construct our own flow of how to solve this. We want to have a control over the process. We want to verify that what's happening inside of this is actually what we want to happen. We have to know when to stop the agent's performance, and we want eventually to try to evaluate how well we performed on the task. Okay, so in our case, the agent's tools should consist of retrieval and answering tools. So if we take the previous graph, the naive graph I've shown you just a few slides before, we can create three types of retrieval tools. First is going to be a retrieval for the quotes, which also want to distill and keep only the relevant content. We want to do the same for the chapter summaries and for the chunks. So this is going to be a group of the retrieval tools that we're going to use. And we also want to have some answering tool, because if we want on the way, on an intermediate step, to ask our data something from the context, from the aggregated context that we are collecting along the way. Or also, when we finish the process, we want to look at all of what we got so far and use this in order to construct our final answer. So this is the second group. Okay. So the whole components that we want to have in order to actually build this is going to be first a planner upon some kind of we want to build a list of steps that we have to perform in order to solve the question, to do A, B, C, D, E, in order to do what the question was. And that's what the agent thinks on the first place, that it's enough for solving the question. Then we want to break down each kind of step to either retrieve or answer tasks, because these are the tools that we have. And then we want to have a task handler that can sort each step to either kind of tool that we have. Then we would want to have a replan mechanism that can look at what we've done so far on the previous steps, on the previous plan, on the context that we have already. And using all of this, it has to decide if we can finish or if we want to update our plan ongoing. And of course, we want to have the two kinds of components of the tools that we described before. Okay. Additionally, I added question anonymization step that tries to generate a more general plan. Because, for example, if we have the question, how did Harry beat Quirrell? So, for example, if we take GPT-4 or any kind of other sophisticated LLM model, it already knows the Harry Potter series and what happens inside. And it might have some biases. If it knows what happened inside, so okay, we're covered. But if it has other biases based on the names or something that he doesn't know, we don't want the plan to be biased from the pre-trained knowledge of the LLM. So in order to tackle this, we want to swap any name entity of the question into some variable. So in this case, we're going to get the anonymized query, how did X beat Y? And by using this anonymized question, we're constructing our plan. And once we get the plan, which is very general, we then replace back our variables to get a general plan with our names. Okay, so this might be a little bit overwhelming, but let's go over this together. So this is the flow that describes the agent's plan, the agent's way to tackle any kind of new question it's going to have. So starting, never mind. So we start with some question, and then we want to anonymize it, and then we are using the planner to construct a plan for the anonymized question. We de-anonymize it, and then we break it down to either retrieve or answer tool. It's behind my head. Then we're going to the task handler that chooses which tool it wants to use, either one kind of the retrieval tools or the answer tool. If it uses one of the retrieval tools, it retrieves and filter out on the non-relevant information and verifies it's grounded on the original context. And if it uses the answer tool here, so it answers some kind of intermediate question it has with the context that it has so far. It verifies it's not hallucination and goes to the replan step from both sides. On the replan steps, it checks if we cannot answer the original question yet, we're going back here. And we do another iteration using the context that we have so far and the updated plan that the replan is constructing for us. And if we can terminate and answer the question already, so we get the final answer, we verify it's not hallucination as well, and then we output the final answer. All right, so how do we know actually when to stop? So I've shown you one way of how to know when to stop. We can ask the replan mechanism every step using the context that we have so far. Can we finish using this context that we have? And if it says yes, we can output the answer, and if not, we can use the replan to update the plan. Other method is to keep collecting relevant data until the process reaches some kind of saturation, which means that the amount of the new interesting information is less than some kind of threshold. And lastly, we can limit the graph recursion by some predefined number of iterations. Let's say after 100 visits in different nodes, we can say, all right, so we cannot deduce the answer from the data, and let's finish here. To evaluate this, since this is actually a RAG task, we can evaluate it similarly to simple RAG tasks. So we want to use the answer correctness measure that measures if the answer is actually factually correct. We want to check the faithfulness, which it checks how well the generated answer is actually based or supported by the retrieved information. We want to check the answer relevancy, which checks how relevant the answer is to the question. And lastly, we can check the similarity by the means of semantic similarity between the generated final answer that you got from the agent and our ground truth. All right, so here we have a short demo. Okay. So we have the question, what is the class that the professor who helped the villain is teaching? So we can see an ongoing visualization of the agent on the top of the screen. And we can see the ongoing plan that we have, the current past steps that we performed, and the aggregated context that we collected so far using our agent with the retrieval tools. I cannot skip this because I don't have access. So we're just gonna wait. 1, 2, 3. So, yes. Simultaneously? What do you mean? So let me finish this and then we have questions, okay? So after finishing all this process, and we have had a very vague first question, and we got the final answer that Professor Quirrell is teaching defense against the dark arts, which can be deduced from the aggregated context that we have here. Okay, so thank you. If you want to contact me, you can use this. And do we have time for questions? Yeah, so can we?
Go back to the... Move from the task handler to table chunk of one of these options.
Mm-hmm.
Why wouldn't it done simultaneously?
Why wouldn't it do it simultaneously?
Retrieve the chunk and retrieve the summary and together at the same time. Why you need just go to one path?
Oh, it's just a matter of design. You can do it either way. Yeah. The question was why wouldn't I retrieve all of them simultaneously, right? All the chunks and summaries and quotes together. So first I did it, but it's also a matter of time and costs. So because you don't have necessarily use all of them, because if you want to look for example, if you want to ask the question about what Hermione said in this and this. So mostly the steps that the planner is going to make is look for what she said here and there and here and there. And so for this, we're gonna use only the quotes retrieval and not the others. So it's going to have a lot of overhead, a lot of garbage. We don't need this. Yes. So you can use, yeah, sure, yeah. So the question was, we have a step in our graph that checks if the question, if the answer is hallucination and how to verify it. So I used LLM as a judge in this case, but I also in some functions, for example, in the keep relevant information. It's also being used by LLM, but in this case, for example, I found out that it will be more useful to ask it to just filter out anything that is not relevant. So in this case, it doesn't make up what it thinks is relevant, but just the final context that you have is going to be included in the original context. Yes? I think it's very, sorry, the question, the question is if using, so let me know if I get your question right. The question was if using such an agent that solves such complex questions, is it cost effective, right? So I will add upon of this the question, is it feasible by times? For example, if you're using RAG for chatbots or whatever, you don't want to wait a lot of times, right? So the answer is it depends. It depends on your use case, I think. If the current solution cannot be solved at all and is going to be solved by some customer support or whatever that's going to take days, and you can use this to solve it within, I don't know, seconds or half a minute, so you can make your own decisions upon this. Yeah, so upon the cost, the same. I mean, if you cannot solve it in any other way, you have to decide if it's worth the cost for solving this. Okay.